Welcome to the physics class for October the 8th. I'm going to do things a little differently today with the quiz. Um, I'm still experimenting with different ways to do it. I've had several people, complain previously that 5 minutes wasn't quite enough time to do the quiz, and I hear you. I understand that. So last time we did a little differently. I gave you 10 minutes. Oh, and by the way, on last time's quiz, one of the questions I had accidentally marked the wrong answer. So if you entered what you were sure was the right answer and Canvas said it was wrong, go back and check again. I have updated it in Canvas now, and Canvas did regrade your test. So you should now have a higher score. Okay, so anyway, with today's quiz, what I'm going to do is I'm going to make it a little bit more challenging, because seeing as how you've got extra time, might as well use it, right? So you see there's a drawback to getting extra time on the test. So the problems on today's quiz are going to be a little bit more challenging. I'm not horribly so, but it might take you more than 10 minutes. So what I've decided to do is I'm removing the time limit, so you can take as much time as you want. And I'm going to make it due the end of the day on Friday, which for those of you in the B-Day class was tomorrow. Those of you in the A-Day class, you might be watching the recording here, so that's why I say it the way I just did. So the quiz, you've got until the close of school on Friday, so that's 3:40 on Friday. Now, remember, Friday is not a day off. Some students seem to think that because we don't hold live Zoom classes on Friday, that means Friday's a day off. It is not. You are supposed to be working on Friday in order to catch up with whatever. So use that time, take the quiz. Also, don't forget that you also have another assignment, which is the test rework. Everybody needs to do that. Even that one of you that got a perfect score and that other one of you who only missed a perfect score by 1 point, even you guys need to retake the test. That's worth 52 points, which is more than 5 times as much as a regular homework assignment is worth. So by all means, make sure you do that. And that is due Saturday at midnight. Okay. So are there any questions about that? Not hearing any, not seeing any. Okay, so let's go ahead and just jump right into the answers to last night's homework. Let me share my screen with you. Okay, here we go. All right, so here are the answers to the problems that you haven't already looked up in the back of the book. Now, some of the problems are a little more challenging today. And if we go over lots of them, I'm afraid we won't have time to. So I'm thinking maybe two questions are all that we're probably going to have time for right now. Anybody have questions about the homework you want to ask?
Can we go over 92?
92? Yes, 92 was definitely the hardest problem. And I will gladly go over that one. Now, because it is the hardest problem, let's hold off on that one. If somebody wants to ask one about an easier problem first, I'll do that, and then we'll come back and do 92. Now, one problem that the other classes, the 8A classes, asked about was problem number 20. That's an elevator problem. You guys want to see that one? Okay, tell you what, let's do that one. AJ, you have a comment? All right. Okay, so let's do 20 and 92. And if you have questions about any of the others, then, oh, I forgot to say, tomorrow, so Friday, even though we're not having an official class, I am going to do a face-to-face Zoom help session tomorrow morning from 9 o'clock until 10:30. I will be here on Zoom just to answer any questions you might have. So if we don't get to all the questions that you have today, come on tomorrow between 9 and 10:30, ask your questions. I'm not going to introduce any new material, so you don't have to attend if you don't want to. But if you'd like a little help, that's available. Okay, so let's look at problem number 20 now. 20 is an elevator problem. So here's the elevator. Here's the bathroom scale. Here's the person standing on the bathroom scale. And so we want to know what is the force that the scale is going to read. So in other words, the force that is pushing up on the person. All right, so let's do a free body diagram. Now, before we do the free body diagram, let's define what our system is. So the force that we are interested in is the force that the scale is exerting on the person. Or you could say that the person is exerting on the scale. What I'm going to do then is I'm going to define the person to be the system. And I'm going to draw all of the forces that are acting on the person, because the force I'm interested in is one of those forces. All right, so let's see. We've got gravity pulling down on the person. And so I could write F gravity. But last time, hopefully you guys agreed that we're going to just go ahead and replace that with the way that you calculate what the force of gravity is. We're just going to call it mg, because the force of gravity is however much mass the person or object has, multiplied by whatever the acceleration is due to gravity on whatever planet you happen to be on, which on Earth is, of course, 9.8. So mg is the force of gravity. So that's pulling the person down, but the person isn't going down, so that means there must be an upward force, and that upward force is, in fact, the scale, which is the force that we're looking for. That's the force of the scale. Right, and those are the only forces that we're interested in. Okay, so our free body diagram, that's the first step. Now the second step is that we are going to use Newton's second law. We're going to say sigma F equals ma, where m is the mass of whatever is the system that we have defined, which in this case is the person. And sigma F is all of the forces that are acting on the object that we've defined. So what I like to do is I like to do little brackets here like that. And then I look at my free body diagram to figure out what goes there. So I see I've got a force right here that needs to go there, and I've got a force right here that needs to go there. That's why it's so important to draw the free body diagram. Right? Now, I need to define my plus direction. Most people like the plus direction to be up. So, okay, let's do that. That means that the force of the scale goes in with a positive sign, and mg goes in with a minus sign because it's pointing down. So Fs minus mg equals ma. And I know what m is, I know what g is, I know what m is. And a, if you look at the problem, they tell you what a is, at least in parts A through D, they tell you what A is. In part E, they don't, which is kind of interesting. But let's do A through D first. All right, so if we know everything except Fs, that means we can just solve for Fs. So let's just add an mg to each side. And that tells us that Fs equals mg plus ma. And bingo, that equation will do everything that we need for all parts of the problem. So let's see, in part A, they say the elevator is moving at constant speed. So if it's moving at constant speed, that means the acceleration is 0. So that means this term goes away. So in that case, the force of the scale is just mg. Okay, it's the same as if the elevator wasn't moving. So it doesn't matter how fast you're moving, what direction you're moving. If you're moving at constant speed, it's exactly the same as if you weren't moving at all. The force of the scale is just mg. Okay, but in part B, we say that the elevator is accelerating. It's slowing down while moving upward. So let's see if we can figure out what that means. So the velocity is going up, but the elevator is slowing down. So that means the acceleration is opposite to the direction of the velocity. So that means the acceleration is in the negative direction. So A here is going to be a negative number. All right. So then the force of the scale is going to be mg plus a negative number. So that means that the answer for part B has to be less than what the answer for part A was. And they tell us what the number is. So all we have to do is just plug in the numbers and we get that. Okay, now for part C, it says that it speeds up while moving downward. Okay, so our velocity now is going in the negative direction. Let's draw a picture of that. So the velocity is going downward and it's speeding up. So that means the acceleration is also going downward. So again, that means the acceleration is a negative number again, just like it was before. And it's accelerating downward at the same rate that it was in part B. So that means the answer for part C has to be the same as the answer for part B, which if you remember from the previous page, it was. Okay. All right, now let's look at part D. So here it says that it's moving downward at a constant speed. Well, if it's a constant speed, then it doesn't matter whether it's moving upward or downward. If it's a constant speed, then the acceleration is 0. And so the force scale is going to be mg, which means the answer for part D had better be the same as the answer for part A was. Otherwise, we did something wrong. Okay. All right, now the interesting one is part E. It says here that it's slowing to a stop at a constant rate of acceleration, but it doesn't tell you what that rate of acceleration is, right? So first off, what direction is it? Okay, so I'm going to have to assume that this is a continuation from the previous part D, where it was moving downward. So if it's moving downward and slowing to a stop, that means that the acceleration, okay, here, I'll do that. So the acceleration is not going to be downward anymore. The acceleration is going to have to be upward, because if it's moving downward and slowing down, that means the acceleration is going to be in a different direction than the velocity. Okay. And so if they don't give us a number for what the acceleration is, then we can't give them a number for the answer. All we have to just do is just use this equation and tell them the answer is whatever mg is plus whatever ma is, but a is going to be a negative number. All right, so let's go back. Let's look at our answers again. Okay, so here are our answers. And okay, so you can see that for part E, the best we could do is we could just say, well, it's this part, which was mg, plus m times a, where a is a positive number. Oh, yeah. Did I say negative? I did say negative, didn't I? I hate it when I do that. If it's moving downward and slowing down, that means the acceleration is in the opposite direction of what the velocity is, which is a positive number, not a negative number. So sorry about that. I hate it when my mouth and my brain aren't connected. Fortunately, that happens a lot. Okay, so there's the answers. And any questions about that before we move on to number 92? All right. Okay, let's move on to number 92. Number 92 was definitely the hardest problem. And it wasn't so much the physics that was hard, although there was a little tricky part that might have stopped you. But for most people, the hard part about number 92 was the mathematics. So let's do it together here. All right. So with number 92, what we have is we have the ceiling, and there's a pulley hanging from the ceiling. And we've got a mast right here. And then the rope goes up and over the pulley and comes down. And then on the other side is another mast. And let's see. One of them is, well, I need my glasses here. Okay, so one of them is a 5 kilogram mass, 5.0, so we have 2 sig figs. And the other one is a 3.0 kilogram mass, right? Now, hopefully you guys realize what's going to happen here is that as soon as we let go of these, the heavier mass is going to start accelerating downward and the lighter mass is going to start accelerating upward. But it's not going to go at 9.8 meters per second because we've got the tension of the rope here slowing that down. Okay, and here the tension of the rope is what's pulling the thing up, fighting against the gravity. So let's do a free body diagram properly. Hopefully you guys remember that the way I like my free body diagrams is I like the forces to be in a different color. So let's just start from scratch here. So here's the ceiling, here's the pulley. Here, let's just call this M1 rather than putting a number on it. Let's just keep it generic. And so this here is M2. All right, so let me switch to a different color for my free body diagrams. All right, so we're going to have a downward force here that is going to be M1 times G. We're going to have an upward force that's going to be the tension. Then tension is just another word that means the force in the rope. So if you pull on a rope, it's undergoing what we call tension forces, being stretched apart. So if you're trying to stretch the rope apart, that means the rope is pulling on you. All right. And over on the other side here, if we look at this guy, the force is on him. We got M2G pulling down, and we got the tension pulling up. Now, one of the things that might have confused some people is it's not at all obvious that the tension over here on the right side and the tension on the left side will be the same. It's not obvious that that's the case. And in fact, if this pulley has friction, or if this pulley has a lot of mass, these two tensions will in fact not be the same. So what we'd have to do is we'd have to call this T1 and we'd have to call this T2. Now, in the University of Utah physics class, they do problems like that. But in this class, we're going to keep things simple. So we are going to assume that this is a frictionless pulley, and it's also a massless pulley. It's made of some material that's so light that we can neglect its mass. So if that's the case, then these two tensions will in fact be equal. So we don't have to call them T1 and T2. We could just call them T, and that's good enough. So if you didn't realize that, then yeah, that would certainly make the problem a lot harder to solve. Okay, so now it's time to start doing Newton's second law and see if we can get some equations that will solve it for us. So let me move this just to make a little room here for us to work. Okay. All right, so let's take Newton's second law. So we got sigma F equals ma, but which m are we talking about? Which f's are we talking about? Well, how about let's focus our attention on m1. So let's define our system. So our system is m1, and so that's all we care about. So we don't even look at m2. It's not part of our system. All right, so when we do the sigma f, so I like to put the little bracket there, and then so one of these forces is going to go in here, and then the other force is going to go in here. That's the whole idea with the brackets there. All right. But before I do that, I need to decide what direction is my positive direction. So let's say that the positive direction is up because we know that's the direction the thing's going to move, right? Okay, so then that means the tension goes in with the plus sign and M1G goes in with the minus sign. And so I bring down my MA, but remember, if we're working with M1, this is going to be M1 times A. All right, so I look at it and I say, okay, I've got an equation. Let's see if we can do it. So I know what M1 is, I know what G is, I know what M was. I don't know what A is. In fact, that's what we're trying to solve. Oh, but I also don't know what T is. Rats. I got two unknowns and only one equation. What to do, what to do. If you got two unknowns, how many equations do you need? Well, you need two. Where could I get another equation from? Anybody got any suggestions?
M2.
Ah, okay, that sounds like a good suggestion. Yeah, we kind of ignored that other mass there. Let's focus our attention on the other mass and see if we can get an equation from that. All right, let me switch to a different color pen here. Okay, so let's define our system now. So our system is M2. So then when I do sigma F equals MA, this time M2 is the one I'm interested in. And so sigma F is the forces that are acting on M2. So let's see. So one of these is going to go under here and the other one is going to go under there like that. And now what I'm about to do is wrong. I'm doing this on purpose because it's a mistake that I suspect many of you made. So don't call it a wig point because I'm doing it on purpose. See if you can figure out what it is that I'm doing wrong. Okay, so tension here, let's put it in with a plus sign because it's going up, right? We defined our plus direction to be up. M2G is, let's put it in with a minus sign, M2G. So that equals M2A. Right? Do you agree with that? By the way, you should not, because I made a very important mistake there on purpose. What is the mistake that I made? In fact, let me share the screen again, just makes it a little easier so you can look at the screen. Anybody see the mistake that I purposely made there?
Yes.
What is it?
So because M2 is heavier than M1, the variables would be swapped. So for example, like M1, you could say T minus mg, but for M2, you have to do negative T plus mg.
You got it exactly right. Yes. And this is a mistake that I see students make all the time. So that's why I purposely made it for you now. When we decided that we wanted the plus direction to be up for M1, that also decided the plus direction for M2. So think of it this way. If M1 were to move in the direction that we have decided is the plus direction, what direction would M2 move in? Would it move up or would it move down? Answer, it would move down. Okay, so the left side and the right side are not completely independent. They are connected. And if we're not consistent, then then we're going to run into problems. So if we chose that the plus direction for the right side was up, that means that the plus direction for the left side has to be down. Otherwise, we're not being consistent. All right, so you are exactly correct in saying that that does change everything here. So that means that this equation here is the wrong equation. It has to be negative t, and it has to be plus M2G equals M2A. All right, so now it's time for my all-time favorite saying that you are going to hear many times before this year is over. From this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Well, let's see how good you are at math. Now, a few of you are still in Math 1, and so you guys are at a definite disadvantage compared to the rest of the students. So the rest of you who are in Math 2 or higher, you have experience solving systems of equations. If you got two equations, two unknowns, you have experience solving these. What are the two methods that your math teacher told you for solving systems of equations? Somebody unmute yourself.
Substitution.
Substitution is one of them. What's the other one?
Elimination.
Elimination. Very good. Now, there is a third one, which is called matrices, matrix math. And that one's actually my favorite. But for some reason, they don't teach that in school anymore, which is a shame. So if you've taken my engineering class or my electronics class, you know how to do matrix math. And so by all means, use that. It's my favorite. Okay, but let's assume that you don't know that. Okay, so now of the two, we could use either one. We could use substitution or elimination. When I look at these, it seems to me that the easier one to use is going to be elimination. So that's the one that I'm going to use, but you don't have to use it if you don't want. You can use substitution if you want. So what I'm going to do then is I am going to take this equation, I'm going to put it over here underneath the other one. That just makes it a little easier to figure out what's going on here. So I'm going to have minus t plus m2g equals m2a. So these are the two equations that I want to solve. And hopefully you guys remember that the way the elimination method works is we're going to take everything on the left side, we're going to combine them together, take everything on the right side and combine them together. Right? When we do that, you'll notice that the plus t and the negative t are going to cancel each other out. Right? That's the reason why I chose to do it this way. That's going to make it just fall out really nice and easy. Okay, so when I put these guys together, what I'm going to get is I'm going to get m2g minus m1g. When I put these two together, I'm going to get m1a plus m2a. All right. Now I'm trying to solve for a. So I got a term here that has an a in it. I got a term here that has an a in it. Hopefully you guys realize that the way to do this is factor out the a. So if I factor out the a, then I get a times m1 plus m2 equals all of that. Okay, and now I can solve for a pretty easily. All I have to do is divide both sides by m1 plus m2. Whatever I do the right side, I have to do the same thing the left side. So m1 plus m2. And so then a then equals that. Okay. We know M1, we know M2, we know G, bingo, plug it in. At this point, it's just plug and chug. And so we get the answer for A. But what about T? The question is also asking us for T. How can we get T? Any suggestions there?
You just plug acceleration back into one of the original two equations.
Exactly. Once we know the acceleration, just plug it in back into either this equation or that equation, whichever was the original equation, just plug it into there and solve for t and bingo, you got it. Yeah. So you see this problem is, yeah, it's a little tricky, I'll admit that, but it's absolutely doable. Okay. So there's our answers. So the tension works out to be 37 and the acceleration works out to be, wait a minute, 2-4? Where did that dash come from? That should be a 2.4. Sorry about that. You know, the funny thing is nobody in the 8A class complained about that. So let me fix that real quick here. Okay. All right. Now, you'll notice that I did it in a different order. The book asked you to solve for T first and then A, but you can do it in any order you want. I thought it was easier to solve it for T, or I thought it was easier to solve it for A first. But you know, you could have done it the other way. That would have been fine. All right, so that's all the time that I really can afford to spend on last night's homework. If you still have some questions, then show up here at my Zoom room tomorrow sometime between 9 and 10:30, and I'll go over any questions you want at that time. All right, let's start talking about the new stuff. So today we are going to go into chapter 5. Let me share my screen here. Okay, so chapter 5, we're going to start dealing now with forces that are in 2 dimensions. Up until now, life has been a little easy. We just had 1-dimensional forces, but the real world is actually 3-dimensional. So we're just going to take a little baby step here. We're only going to go to 2 dimensions. And in fact, in the high school physics class here, we only do stuff in 2 dimensions. But when you take the University of Utah physics class next year, which I hope you all will, you'll be working in 3 dimensions there. It's actually not that bad. If you can do 2, doing the step to 3 is not bad at all. All right, Now, the way that I would like to do this is by using a sailing example. By now, you guys have probably figured out that, in my opinion, the best way to learn physics is to go sailing. So that's what we're going to do in order to learn today's material. We are going to plan a sailing trip. Let's see. So let's say we want to go, let me get out Google Maps here. Okay. All right. And we don't, okay, we don't want that. Okay, so let me just zoom out real fast. Come on. Okay, sorry. Okay, there we are. Okay, so let's say that we want to sail to a set of islands that is off the Florida coast. It's called the Bahamas. So you see this group of islands right there? Those are called the Bahamas. And if any of you have ever been there, then you know that they are really beautiful. Oh, so nice. If you ever get a chance to go to the Bahamas, I absolutely highly encourage it. You'll love it. All right, so we are going to go to one particular island. It's an island that's so small that you don't even see it right now because there's a whole bunch of Bahama islands. I'm going to keep zooming in. And there, you see that island that just appeared right there? That's the one that I want us to plan a trip to. All right, so that island is called Bimini. Let me turn on my sharing here, or turn on my my screen. My annotation is what I meant to say. Okay, so this island here is called Bimini. And you'll notice that it is located pretty much exactly east of Miami, which works out to be kind of nice. All right, so let's suppose that we were to measure that distance, right? Boy, I'm not sure if that yellow shows up very well. Let me switch to red. Okay, so if you measure that distance, you'll see that it's 50 miles. Now, sailors normally measure distances in what are called nautical miles, which are slightly different than the miles that you're used to, but not much. It's only about 15% difference. So I'm just going to call it a mile, even though it's actually a nautical mile, and let's not worry about that. All right, so notice that it's 50 miles and it's pretty much exactly straight east. So we're going to plan a trip and we need to estimate how fast we're going to go. And with a sailboat, it's kind of difficult to predict in advance how fast it's going to go because it depends on the wind speed. But a good number that works pretty well for planning purposes is about 5 miles per hour. And that's nautical miles per hour. So that's 5 knots is the way that a sailor would say that. But let's not worry about it. Let's just say it's 5 miles per hour. That's a pretty good average for what a sailboat would go. All right, so here's a question that I want to ask you guys. And so what I'd like you to do is type your answer into the chat box and type it in privately so that only you and I can see it. 2 questions. Question number 1, what direction should we point the boat in order to go from Miami over to Bimini? And question number 2, how much time will it take us to get there? All right, everybody, please type in your answers into the chat box privately. Okay, I'm seeing 2 answers, 3 answers. Okay. All right, it looks like everybody is agreed. Okay, so it looks like everybody's in agreement that what we should do is we should point the boat east, and everybody's in agreement that it will take 10 hours to get there. Well, I got bad news for you guys. If we were to do this, okay, and by the way, I have done it many times. If you leave Miami and you point the boat east and you sail for 10 hours, then you say, okay, we should be there. Where's the island? I'm not seeing the island. So, well, maybe we're going a little slower than usual. So I'll go for another hour. Still no island. Another hour. Still no island. we missed the island. Okay. What went wrong? Anybody got any ideas on why we would miss the island if we point our boat east?
Would it be because like the water, um, like flows? You wouldn't go directly east. It would make you move another direction.
Yes, that is exactly right. Okay. There is a current that's a very famous current. It's called the Gulf Stream. And I'm sure that you guys have heard about the Gulf Stream because there's a song that pretty much everybody that I've ever met that went to elementary school here in America, or here in Utah, at least, you sang the song. You heard, "This land is your land, this land is my land." Does that sound familiar? Did you learn that in elementary school? There's one line in that song that says, "From the redwood forest to the Gulf Stream waters, this land is made for you and me." That sound familiar? Okay, so the Gulf Stream is actually a very, very famous current. And so the water in between Florida and the Bahamas is moving to, oops, so you need to switch over to annotate mode before I go touching my screen. Okay. And let's make it yellow, see if that shows up better. Oh no, we decided it didn't. Okay. All right, so the water is moving to the north at a speed of about 3 miles per hour. And that's nautical miles, so really it's 3 knots is the way that a sailor would do it. But let's not get hung up on knots. Let's just call it 3 miles per hour. Okay, so if you point your boat east, but the water is carrying you north, okay, you're going to end up going northeast-ish. Now, I don't want to say northeast because if I say northeast, that has a very definite meaning. If you say northeast, what that means is that this angle right here is 45 degrees. Okay, and this angle here is not going to be 45 degrees. So I'm not going to call it northeast, but I will call it northeast-ish. Right. So if you are a sailor, you need to know how to deal with this situation. Basically, what we're doing is we're adding vectors, okay? And so adding vectors is a skill that you need to be very, very good at in order to pass this class. We're going to be adding vectors all year long. So remember how we said that 2 + 2 is not necessarily 4? Well, okay, so this is the perfect example of that. Now, if you're a sailor, your life literally depends on being able to add vectors and figure this out, because if you can't do it, you don't account for the current right, and you're sailing to some island that's pretty far away, you might miss the island, and then you're in trouble. You run out of food and water and you die. So your life literally depends on being able to add vectors. But the interesting thing is that most sailors I know cannot do math to save their lives. And yet they need to do vectors in order to save their lives. So how do you add vectors if you don't know math? Well, here is how we do it. I'm going to show you how to add vectors without doing math. Okay. Okay. All right. Whoops. Why did it do that? Let me come back into here again. Okay. So what we're going to do is we're just going to use graph paper, and you're going to see that that protractor that down in the corner there is going to come in really handy in a minute. All right. So what sailors do when they need to figure out problems like this is they just get out a bunch of graph paper, and then they draw arrows on the graph paper. So the arrow, we're going to make it so that the arrow, the length of the arrow corresponds to how fast the different velocity vectors are. So the boat, we decided, was moving at 5 nautical miles per hour. So I want to make this arrow here so that it's exactly 5 long. So 1, 2, 3, 4, 5. Okay. So this horizontal arrow there, that represents the speed of the boat through the water if the water is not moving. But in fact, we know that the water is moving. We know that at the same time that the boat is moving to the east through the water is also moving to the north. And so we need to adjust this arrow so that it's the right arrow for the water speed, which you remember we said was 3 nautical miles per hour. So 1, 2, 3. Okay, so what you see here on the screen right now, that represents what is happening to the boat. We've got 2 vectors that are both acting on the boat at the same time. Now, here's the trick. When sailors add vectors, what they do is they don't draw it this way. They take one of the vectors and they move it over here so that the second vector starts where the first vector ended. Okay, even though what you see right here, this better represents what's actually happening. When a sailor adds vectors, they draw the one vector, and then the second vector, they draw it so that it starts where the first vector ended. All right, so now what we can do is we can say that the resultant velocity is the vector that starts where they started and ends where they ended and doesn't care what happened in between. That right there is what we call V resultant. Okay, that is what direction the boat is actually going to go. And you can see it's not 45 degrees. All right, so if this side of our triangle, oops, that's not 3, that's 5, sorry. So this side of our triangle here is 5 miles per hour. This side of our triangle is 3 miles per hour. So our job then is to figure out how long that red vector is. Now, you guys are all really good at math. So I'm sure you know, well, hey, that's easy. Just use the Pythagorean theorem and voila, you got it. But sailors suck at math. They couldn't do math to save their lives. But like I said before, they can do vectors to save their lives. So how can they do vectors? Well, okay, here's what they're going to do. So so what I've done here is I've taken a little piece of graph paper, right? And so I just take a piece of the graph paper and I tear off a little strip, and then I position it at the right angle and I lay it right over here so that it starts right here where they start and it ends right here where they ended. And what you can see, let me turn on annotation here. Okay, what you can see is that it's 1, 2, 3, 4, 5. It's a little bit less than 6, right? So it's a little bit less than 6. And in fact, if you really look at it closely, I would call it about 5.8, right? So what that tells me is if I add this vector and this vector, the resultant vector is a vector that is 5.8. So that tells me how fast the boat would actually go. Even though, when I look at the boat's speedometer, which basically it measures the speed of the boat through the water, the speedometer is telling me that we're going at 5 miles per hour, but in reality, we're going at 5.8 miles per hour. Okay, now those of you guys who know the Pythagorean theorem, which had better be all of you, has anybody punched out the numbers yet to see what number you get when you use Pythagorean theorem?
Oh yeah, it's 5.8. 3.
And can you give me one more sig fig?
It's 5.830.
Okay, good. All right, so if we round it off to 2 sig figs, look at that. So the Saylor method actually works really, really well. So if you're a sailor, you don't need to know the Pythagorean theorem. If you just use this Saylor method here, it works wonderfully. Now, remember that velocity is a vector. So if we calculate the magnitude, which we just did, we haven't completely done the job because a vector has both magnitude and direction. So what we need to do is we not only need to figure out what the magnitude of the vector is, we also need to know the direction. So if you're a sailor who doesn't know math, how are you going to do it? Well, the protractor. Okay, let's get the protractor here and let's zoom in on it. Okay, and let's position the protractor in the right place. Okay, so it looks to me like it's a little bit more than 30, right? So if you're a sailor, that's good enough. I mean, you don't need supreme accuracy. Ah, but you guys are not sailors. You guys are physicists. You know math. All right. So we can figure out what that angle is using mathematics. Has anybody figured it out yet? What would, sorry about the noise there. It's the landscapers working outside. Okay, so if this side here is 5 and this side here is 3, I want to know what is this angle. How would we do that? Anybody got suggestions? We're going to need to use trigonometry. So which one of our 3 friends is going to help us out here? Okay, tangent is what I'm seeing in the chat box here. So let me go to a whiteboard here, just make it a little less clutter, easier to focus on what we're doing here. Okay, so if we have a triangle where this side is 5, this side is 3, and our resultant is this guy right here, which we know is now 5.8 something. All right, so Max is suggesting we could use the tangent property to find out what theta is. So you guys, you need to have these memorized. So if you don't already have it memorized, get out a notebook right now, get out some flashcards. Remember, sine, cosine, tangent, you need to know those definitions without any hesitation. All right, so Max is suggesting we use the tangent. So the tangent of theta is equal to the opposite side divided by the adjacent side, right? So we know what the opposite side is. We know what the adjacent side is. We're looking to find out what tangent is. I'm thinking that's going to work. Okay, so that means that the tangent of theta is the opposite side, which is 3, divided by the adjacent side, which is 5. But we don't want tangent theta, we want theta. So how do we get rid of that tangent? Well, hopefully you guys remember that what we do is we take the inverse tangent of it. Inverse tangent kills tangent, leaves us with theta. But the rules of math say that whatever we do the right side, or left side, we have to do the same thing the right side. So it means theta then equals the inverse tangent of 3/5. All right, so has anybody punched that into their calculator yet? When somebody punch it in, tell me what you get. Ah, okay. So it looks like, oh, let's see. I think some of you might be in radians. I want to know what the angle is in degrees, not in radians. So AJ is saying that it's 30.96, which is more sig figs than we're allowed, but that's okay. I mean, okay. So that rounds off to 31. So theta, then if we go with 2 sig figs, so let's say this is 5.0 and 3.0. That way we're allowed 2 sig figs. So guess what? Theta is a little bit more than 30. So the Sailor method, where we just put the protractor there and measured it, that worked great. But you guys can do better. You guys, you should be able to use sines, cosines, tangents. You need to be really good at those. All right, so what we've done here is we've added some vectors. And in your homework tonight, you're going to have practice adding vectors, doing problems like this. You're also going to have problems where you go the other way. You take, instead of taking 2 vectors where your vectors are nice and perfectly, either a perfectly east vector or a perfectly north vector, sometimes you're going to have to deal with vectors that I like to call funky vectors. Because instead of going perfectly east or perfectly north or perfectly south or perfectly west, they go off at some funky angle. And you guys need to be able to deal with these funky vectors. So let's do an example here. Let's say that we've got here's our north, south, east, west cross there, which you guys need to be really familiar with that. All right, so let's suppose that we've got a vector that goes off like this. And let's suppose that this angle here is, oh, I don't know, let's just say is 26 degrees. I'm just making up numbers here. And let's say that the length of the vector is 129 whatever units it is we're working with. Now, you guys need to be aware that what we're doing right here works for any kind of vector. It could be a velocity vector like the ones we just worked with, but it doesn't have to be. It also could be a force vector, could be a displacement vector, could be any kind of vector you want. It works for all of them. So let's say that we've got a situation like this. Let's say it's a force vector this time. Okay, so that's going to be 120 newtons is what it's going to be. And so what we want to do is we want to come up with two non-funky component vectors that do the same thing as our funky real vector. So what I mean by that is if I were to have a vector that went purely east, and then we turn and we have a vector that goes purely north, hopefully you can see that these two red vectors do the same thing that one kind of bluish pink, I don't know what color you call that. Let's just say bluish vector. Okay, they accomplish the same goal. So these red ones, those are called the components of the funky vector. And so in your homework tonight, you're going to have to figure out what number those would have to be. So if we call this X and we call this Y, your job is to figure out what number would X have to be, what number would Y have to be, so that when you take the two component vectors and add them together, they do the same thing that one funky vector does. All right, so let's start with the X. If I know the angle and I know the hypotenuse, X here, okay, which is the adjacent side, that's what I'm looking for. So anybody have any suggestion which one of our three friends is going to help us out? Should we be using the sine? Should we be using the cosine? Should we be using the tangent? All right, looks like you guys are in agreement. Cosine is what we want. Okay, very good. Glad to see that. All right, so then we're going to say the cosine of theta is defined as the adjacent divided by the hypotenuse. Okay, so let's put in the numbers then that we know anyway. So the cosine of 26 then is the adjacent, which we don't know, so we'll just have to call that X, over the hypotenuse, which we do know, which is 120. All right, so now all we have to do is just make our math teacher happy, shows we know how to solve for X. So if we multiply both sides by 120, that goes away. So X then is 120 times the cosine of 26. Can somebody punch that out and tell me what you get? Come on, somebody punch it out here. Okay, so 107.855. Very good. Okay, now with sig figs, we would have to round that off. We're not allowed that many sig figs, but let's not worry about that right now. Let's say if we were allowed to have all those sig figs, that is what X would have to be in order for this to work out. Okay, what about Y? All right, so let me switch to a different color here. All right, so now I want to focus on Y. Which one of our three friends is going to help us out? Sine, cosine, tangent. All right, so I see AJ is suggesting we use the sine. Now, some of you are going to say, well, hey, now that we know two of the three sides, we could use the Pythagorean theorem to solve it. And you are correct in doing that. But I would rather just use trig functions. Okay, so AJ is suggesting we use the sine. So we know that the sine of theta is defined as the opposite side divided by the hypotenuse. All right, so let's go ahead and put in the numbers. So the sine of the angle, which we know is 26 degrees, must be equal to the opposite, which we don't know, so we called that y, divided by the hypotenuse, which we do know is 120. So then if we multiply both sides by 120, so then y is equal to 120 times the sine of 26. Somebody punch that out and tell me what you get. All right, so it looks like 52.6 is what people are saying. Okay, very good. So what that means then is that if we have this funky vector over here that is 120 newtons, that's going off at an angle of 26 degrees north of east, note the way that I said that, okay? So then that would be the same thing as if we had two component vectors, where one of them is 108 newtons that's pulling straight to the east, and the other one is 53 newtons that's pulling straight to the north. These two red vectors do the same thing as the blue vector does, so those are called the components. Okay. Now I have a special name that I like for this. This is just a Hendrix name. If you go to any other school, people are going to look at you weird. But what I like to do is I like to say this vector right here is a funky vector because it's not going in a nice direction. It's not going straight north, straight east, straight west, straight south. It's going in a funky direction. So I call it a funky vector. So when we break it up into the components, what I like to do is, or what I like to say is I say that we're going to defunkify this vector. But that's just a Hendrix term. If you go to any other school, people are going to look at you really weird if you say that. Unless you go to the University of Utah. We've had so many AIM students come out of here and go to the University of Utah that the professors up there, if you talk about defunkifying a vector, they're going to look at you and they're going to say, ah, you obviously went to AIMS, didn't you? Okay. All right. So that, if you understand that, I think you're going to be pretty good with tonight's homework. Basically, what you're either going to do is you're going to take non-funky components and you're going to put them together to create a funky resultant vector, or you're going to start off with a funky vector, and then your job is to defunkify it. In other words, break it up into its components. Now, you might be adding vectors. So if you have to add vectors, well, one way to do it is get out some graph paper and do it the Saylor way. That won't be as precise as you might need, but it works. But the better way is to get out your math skills, use the Pythagorean theorem, use your tangent definitions, and I think you'll be good with that. All right, so before I turn you loose to do the homework, because remember, class is not over. We still got 20 minutes left. Okay, so that's plenty of time. Before I turn you loose, do you have any questions? Not hearing any, not seeing any. Okay, tell you what I'm going to do. I'm going to turn off the recording so that if you had a question but you didn't want to ask because you knew it was being recorded, I'll turn off the recording so that you can ask. But if you don't have any questions, just go ahead and type bye into the chat box. But remember, you have a quiz to take. And that quiz is probably going to take you between 10 and 15 minutes. So now would be a good time to use that time to do that. Also, don't forget that you need to redo the test. Even those of you that got A's on the test, you need to redo it too. And so the quiz needs to be done by the end of the day tomorrow, by the end of the school day tomorrow, by 3:40 tomorrow. And then the test rework needs to be done by midnight on Saturday. Okay, so I'm going to go ahead and stop the recording.